Hello again, and welcome to Environmental Geology. This is Lecture 3, and we're going to be focusing on the topic of tectonics and earthquakes. And so the next several lectures, in fact, we will be working on this subject. So today will be kind of an introduction to the concepts that are behind plate tectonics and a little bit about earthquakes and some of the other associated phenomenon. You should be focusing on Abbott, the text chapter 2 in the Primus book to be able to keep up with this. Okay? So I think the first thing that we think about with earthquakes is the fact that it's a geohazard. We're always seeing all the news media of all the problems of damaged buildings and destruction to structures and the loss of life associated with that. And so we're going to try to focus on some of the reasons why behind this. We'll get into more of the detail on seismology in the next lecture or two. And I have the phrase or the word tectonics. We could also maybe think of that as plate tectonics. And so the focus at the beginning of this topic today is going to be about plate tectonics and a little bit of the history behind it. So really, what is plate tectonics? Plate tectonics today is a theory. It was a hypothesis that began in about the 1960s and has progressed to become a theory. But prior to that, this theory of plate tectonics really evolved out of two different hypotheses that were proposed in geology. The first hypothesis dealt with continental drift. And that hypothesis had some weak spots. And then about 40 years, 50 years went by, and then we came across some new data, led us to a second hypothesis called seafloor spreading. So I thought we'd look at these two different backgrounds on these hypotheses and just briefly look at where they came from and some of the research behind it that eventually led to this concept of plate tectonics. Let's first look at the idea of continental drift. There was a gentleman by the name of Alfred Wegener back in the early 1900s at a meeting who, a science meeting, proposed at a talk that the continents, all the major continents of the world, had actually been drifting and moving across the surface of the earth for about the last 200 million years. He said that they moved. Now, the map you see here is really a more modern-day map of the present positions of the continents today, and even more information than what Wegener certainly had as far as continents. Now, you have to think about 1915 and what we knew about the world. We were beginning to learn a lot about what was on the land, but we didn't know a lot about what made up the seafloor at that time. And it took quite a while before we came up with new technology and instruments to work on that. So how did they go about working with continental drift? What was it that Wegener proposed? Well, he started out looking at continents in terms of their shapes. If you were to take a world globe today and cut out the continents like Africa and South America and North America and so on, and like a jigsaw puzzle, try to maybe piece them together, because as you look at a globe, you could say, you know, I could take South America and kind of tuck it into the margin, the western margin of Africa. It seems like it would fit like a jigsaw puzzle. That's kind of the way they looked at it. Of course, they had a little more information about it, and I'll outline that in a bit, but this was the idea of best fits, the idea that we could kind of fit these pieces of the puzzle together. Now, there were overlap spots, there were gaps that could not be explained at this time. But there was other evidence that Wegener and his colleagues said that could support the idea that these continents were actually together and joined as one large landmass or several large landmasses at some point in the past. So besides the best fit, they also talked about once you fit those continents together in a bigger piece as the puzzle was put together, that a lot of the rock types along the margin of the continents, the igneous, the sedimentary, and the metamorphic rock types, as well as their structural orientations, their compass directions, when you put them back together, they fit and lined up as well, just like putting the rifling and matching a bullet to a particular gun, that you could match that and they line up. So it wasn't just fitting edges of a piece of jagged, continents. It was also rock types that made up those continents. It was also the orientation and the structure of those rocks. The last evidence that they also used to support this was fossil material. Particular types of species that were only terrestrial or landlocked freshwater creatures. The idea for those critters to evolve, those land masses had to have been together as one large piece. Now, I'm going to introduce a new word to your vocabulary. I want you to write down the word Pangea. And this term that Wegener used meant all lands. All of the major continents as one major landmass was referred to as Pangea. At that time, of course, the ocean, we didn't have really a true Pacific Ocean per se or an Atlantic Ocean. They evolved. But what Wegener said is that around 200 million years ago, this large landmass, Pangea, existed, and then it split up. Not all at one time. Little pieces began to pull apart from others at different rates and spread apart. And here's kind of another view off of a U.S. Geological Survey map of the same kind of thing, showing us the fossil type evidence where the different species, whether they be mammals or plant types, could only exist and evolve genetically in the terms of the genome pool as if they were on the same landmass. You can't have some freshwater organism swimming all the way across the Atlantic Ocean and breeding and reproducing and then swimming back and evolving in the same exact manner. It just does not work biologically. So the biological evidence, the structural evidence, the rock type evidence, the best fit evidence, as well as another thing I didn't put in the list was those rock types form in warm climates, cold climates, wet climates, dry climates. When you match those land boundaries up, the same thing happens. They all fit. And as you trace them through time, evolution changes in the species. Things became separated. The gene pool was separated. The rock types are split apart. And they're still moving today. And so if we look kind of at a collage of some of these, when Pangea began to split up, there were land masses that were more so in the northern hemisphere. And so we had our scientists in the northern hemisphere kind of competing against the scientists in the southern hemisphere. They had people in the southern hemisphere say, well, we got this big landmass down here. We're going to call it Gondwana land. South America and Africa and Antarctica and Australia mainly, maybe India as well. And not to be outdone, the northern hemisphere scientists and geologists said, well, we have one too we can prove fit together, Europe and Asia and North America. And so we're going to call ours Laurasia. There was kind of a little bit of political gamemanship going on to some extent in the science realm, but it was Wegener who brought it together and said, look, there was one large landmass. As it began to split up, some of those spread more towards the north. We'll call that Laurasia, that's fine. Those that went more towards the southern hemisphere, we'll call Gondwana land. And as you can see from all the arrows kind of drawn on here, that the general directions that these pieces of the puzzle, these continental masses, began to move apart. Now, this was a nice proposal that was presented, but there was a big problem. At that particular time, based upon knowledge we did not have about the seafloor, about the interior of the earth in particular, because somebody said, well, how do you make them move? And Wegener says, I don't know. I don't have a mechanism. So it kind of went by the wayside for a while, and that continental drift hypothesis somewhat sat there for about 45 years, in fact. So there was no mechanism to move them in his scientific kind of outline. So 45 years went by. In that time period, of course, several wars passed. And in particular, in World War II, we developed some extremely useful types of technology to locate things on the seafloor, particularly U-boats. Certain kinds of pingers and radar technologies and so on was not only helping us in the war effort, but also gave us instruments to see what the topography of the seafloor was. And little by little, this data began to build up. Okay? Now, after the war's over, we've got a lot of people from the Navy are out there going into oceanography, physical oceanography in particular, and they began to map the topography of the seafloor, and they began to see that there were very large mountain systems, high elevations, mountain ranges along some of the central parts of the ocean bottoms. In fact, the outline and shape almost seemed to kind of match some of the boundaries, again, of these continents on either side of them. And they said, well, this is more than a coincidence. But that's as far as they got. They said, well, let's get down there. Let's start to research this some more. So as the 1960s roll about, okay, then we began to gather a lot of data. We not only had better maps of what the seafloor topography was like, we also began to collect data on rock types on the seafloor, heat measurements on the seafloor, magnetic data on the seafloor. And we know that some of the things we could measure on the land, like over here in this picture on the bottom left, we've got a series of layered extrusive basaltic lava flows. And you go in there and you collect those rocks, you can measure paleomagnetic data, ancient magnetic data locked in certain minerals in those rock layers. And of course, you know by using a compass that magnetic north is, the needle points to a certain direction. Okay? Positive end, negative end to that needle. Well, it turns out that we can find that same kind of information locked up at ancient rocks that we can age date. So we could go back 100 million, 200 million, 300 million years ago, and in these lava flows on the land, measure the differences in terms of the strength of the magnetic fields, which way the needles pointed, and we found out sometimes the positive and the negative ends of the Earth's magnetic field had flipped, had reversed themselves. So we had another kind of little bit of information to say, we're beginning to see some patterns on the lava flows and the polarity on land, as well as patterns to the same kind of lava-like extrusive basalts that make up the seafloor, and they're matching. They're the same thing. We're seeing parallel patterns of magnetic reversals on the seafloor, and they said, why? How come? What's going on here? Something was happening here in the middle of the ocean basins along those high ridges that were topographically high. We not only saw that they were much warmer down here, higher heat measurements. As we looked at the cores, we saw that the sedimentary rocks got thicker and thicker and thicker away from the ridges in a nice symmetrical pattern. We saw that the temperature of the basalts got colder away from there. We saw that the ages of those rocks got older and older and older. And all of this was symmetrical patterns away from those central ridges. What did that mean? That's what these oceanographers were asking. Well, little by little, they proposed this concept that, what's happening is we've got cracks in the outer part of the Earth in some of these places on the seafloor where magma's oozing out, and then it's moving away from these central ridges or these rifts. It's splitting. It's spreading apart. Thus, this phrase or hypothesis, seafloor spreading. So in the 1960s, everybody got really fired up. And more research in oceanography and wanting to get down there and see firsthand what was going on in these places. Now here are some newer images we have of radar type images, a kind of a side angle view of the topography of the seafloor, a major ridge, little seamounts and volcanoes on the bottom of the seafloor. We can see that some of these ridges here are completely offset by another type of pattern. Eventually we see that these are faults and cracks that are moving at different speeds and spreading apart at different rates. So we began to come up with how fast these things are splitting and moving apart. Somebody says, you know what? This sounds like a mechanism to move something. This may be the mechanism that's causing the continents to split and move apart throughout time that Wegener proposed 45 years prior to this. Let's go after some more data. Let's get a little submarine and go down there and look around. Let's collect some more rocks and some more data. And so subsequently, from 1960s up until now, the database and the images and the new ideas that we're finding out about the seafloor are just tremendous. So from the 60s into the 70s, that hypothesis of looking at continental drift and the seafloor, they said, let's put this together. We're going to call this plate tectonics. Okay, we know more about the ideas of the driving mechanisms behind this now. So it became a theory at that point in time, as more and more geologists tested the hypotheses and put them together. The little inset picture here shows you some interesting things we'll look at more closely later on. If you get in a submarine and go down into these rift systems down here and take some pictures of strange things. There's a big pagonophoran worm tubes. Here's a little crab. You can see some of these later on. Here's a newer, fancier, higher resolution image, a radar, side scan radar image of another part of the seafloor in a big rift system. But look at the detail in the topography that we're picking up on. So in a short time, we're just kind of snowballing in our information. Well, at Scripps Oceanographic Institute, along with some French researchers, they built a little submarine, hopefully not influenced by the yellow submarine of the Beatles, but Alvin, okay? A little submersible, got 2 medium-sized people in it, maybe 3 small people. Pretty confined spaces, and just let you sink like a rock about 18,000 feet below the surface of the earth and go down there and see what they could find. Well, it was amazing. In this shot, you can see in this in the center part some fresh, brand new black basaltic lava that oozed out on the seafloor, and giant clams, a foot, foot and a half long, whole new species of clams that we never saw before, and much, much more. Here are these clams here, kind of a scale. You can even go down in the bottom of the Sea of Cortez, or the Gulf of California as we call it, and there's these little mountainous rift systems down there. They're all over the place that we're studying, from off the coast of Oregon to the Middle Atlantic to the Indian Ocean. More and more researchers are involved, and look at some of the interesting things in this this collage of things. Besides those worm tubes, here we've got a giant kind of crab, long-legged crab. More of these worm tubes. You can see lots of little smaller species of crabs on them. An anemone. The yellow stuff on this lava is sulfur, very, very rich in minerals of sulfur. A lot of things are venting out on these sea floors and coming out with that hot lava. Iron and nickel, manganese, silver, gold. Here's some nodules filled with pyrite, some sulfide type things. And here's a scanning electron microscope image of some crystals associated with bacteria, anaerobic bacteria. We're down 18,000 feet. There's no oxygen. There's no sunlight. A totally different ecosystem. Now, this is more of biology of it, not so much natural hazards, but something's happening down there. And it took a lot of scientists to head on into this region of the world. Here's something new came out in the 1990s. Had a satellite going over the Earth. It had a gravity meter built in for an altimeter. And it was measuring the elevations of the sea surface. And as currents and the ocean masses move around and are, they're affected by gravitational pulls of the rocks beneath them. Depends on the topography. So what we were really seeing by mapping the detail of the surface of the oceans was really, through gravity, a super high-resolution detailed map of the seafloor. So after we had all those radar images and other stuff, now we got something up in space, looking down, and more of the pieces of the puzzle are coming into view, things that we didn't find because an oceanographic ship didn't cover every spot on the ocean. Now we have total 100% coverage. Extreme detail in these mid-ocean rift systems, the fractures that are parallel to them, a series of islands like the Hawaiian Island chain that then takes a short bend into the Imperial Seamounts and all of a sudden disappears into the Aleutian Trench. Why this topography? Here's a line of aseismic, meaning no earthquake activity, of a ridge. It's called the East 90 Ridge in the Indian Ocean. No volcanoes right now at this time, but turns out as the chunk of India broke off from Pangaea and Gondwana land and blew northward, that kind of represents a trail of it in the seafloor. So we began to find more and more evidence to continually support this concept, this idea of plate tectonics, that things were moving around. So I always like to use another analogy to think about it. We know that plate tectonics is a very real, workable hypothesis to explain a lot of things about earthquakes, about volcanoes, about crumpled mountain belts, about folded metamorphic rock systems, about the distribution of oil and gas. So the way I like to think about it is a demolition derby. You know, if you've ever been in active contact sports and you get hit, you know that something could get broken or bent. If you've been in a car accident, you can see the obvious. Now, besides the crumpled fender, you might see a big streak of red paint off of somebody else's car on the side of yours. Something from another continent, an automobile, got stuck on your continent, your car. So the idea of a demolition derby, that's all plate tectonics is in a way, except it's slow in terms of time for us, but it involves masses of rock, continents. So different parts of the earth. So our next step is to really begin to take a step back and look at the inside of the earth and see how it evolved, and maybe a closer look at where these mechanisms are coming from. All right, so let's kind of go back in time and talk about the early formation of the earth. As all that material coalesces through gravitational collapse in the very beginning, about 4.6 billion years ago, a lot of those materials we could call meteors, this accretion of celestial material, coalesced and became our planet. There was a lot of frictional heat that built up. So the initial Earth had heat in it. There was a tremendous amount of heat created by that. And so things could melt. Things could begin to separate chemically. That initial homogeneous mass of material began to separate. The heavy elements in the periodic chart we talk about, like iron, iron sank to the center of the Earth. Lighter weight materials like silicon and aluminum and so on were further out, away from there. The gases would move all the way out to the outside, kind of an outgassing process. So as the Earth formed, it had its initial heat in the beginning, but other elements inside the Earth, of course, also produced energy. Radioactivity, as we said earlier, is a form of heat. So there are heat sources inside the Earth, and it began to separate into different parts. So let's take a look at some of these parts. The innermost part of the Earth is mostly iron. There are some nickel and other elements down there, but mostly iron, and it's solid. The temperatures are extremely high in the center of the Earth, but that's solid because the pressures are so high there, the atoms cannot pull apart and liquefy. But as you move away from the center of the Earth, the pressures are reduced, and therefore melting points are passed, and this zone of iron, of course, then liquefies. And so we have a liquid outer core and a solid inner core of mostly iron. Now let's take another kind of view of what the Earth really is. That opening slide we had today that showed the Earth spinning. The Earth revolves on its axis, spins on its axis. And so here we have this spinning liquid metal. That spinning liquid metal, we know, even in a laboratory condition, can produce an electrical field which produces a magnetic field. It's this right here that causes the Earth's magnetic field, this spinning character. All right? All right, now as you move away from that core region, you go through some lighter elements that make up the mantle, and finally kind of to that thin outer candy shell of the Earth, and we've got a bunch of other names for it I'll go into with another diagram, the crust, the lithosphere, the asthenosphere, and so on. Okay? But we realize that heat is moving outward from the center of the Earth. It's moving out in different ways, different fashions that are probably creating, or which are creating, these driving mechanisms for plate tectonics. So here's another view of a figure from your textbook. And let's look at how they divide this thing up. The right-hand portion of this refers to the density characteristics of the elements, how they're compressed. So the most dense material is in the innermost core. And as you go outward, it becomes less and less and less dense as we get on the outside crustal portion of the Earth. Okay? It's this spinning iron, liquid iron that creates the magnetic field, which is a dipolar type of magnet, meaning it's got a positive end and a negative end to it. And we'll look at some pretty spectacular pictures that are evidence and proof of that we have a magnetic field. Okay? But as you move from the solid inner core, you move to the liquid outer core, which, again, it's liquid. It has a more viscous character to it. or less viscous, like lower viscosity like in magmas. And as you move back into the mantle, it's solid again. But through the process of conduction, this hot inner Earth is conducting heat from the inside towards the outside. It's heating up different zones in the mantle. So in some places in the mantle, in the lower mantle, those masses of rocks can get heated up. And what happens to things when you heat them up? Well, and not melt them. You can just, let's just say we just heat them up. What can happen is you can cause them to expand. And things that expand, what happens to their density? They become less dense. So there are zones and pockets here in the lower mantle that we began to propose that are hotter, i.e. hot spots, that are slowly rising like a hot oil lamp today towards the surface. So that's a process of convection. So a second way of bringing heat from the inside towards the outside and bring it towards the surface is convection. So something begins to happen up here in the upper mantle, lower part underneath the crust, that is part of this process that drives and moves the plates. So before we kind of look into some of that, let's look at this magnetic field a little bit, about some of the other kinds of evidence that are out there that, you know, these invisible magnetic force lines are there. And if you ever have a chance to go up in space and take a look at this from there, the astronaut's point of view, these are the aurora borealis, the northern lights as viewed from space. Quite spectacular, and you can see these lines and these color differences. What's happening is there's solar wind. There's particles from the sun that enter our magnetic field of the Earth, get trapped in it, and those force lines pull those particles down through our atmosphere, and they hit oxygen, they hit carbon dioxide, they hit nitrogen. And they excite those gases and create all those beautiful colors that you see. Pretty spectacular kinds of conditions. Here's what it looks like, of course, or one of the views of what it looks like from the surface of the Earth. So we have the northern lights, we have the southern lights as well, as energy is brought into it. Now where that begins is right here on the sun. Huge storms on the sun. These are the sunspots that we see. This is just last fall. We had a pretty big magnetic storm due to the sunspots on the surface of the sun, and of course that energy that blasts away, even the sun has its own magnetic field, and you can see some of the particles blowing out of there from the sun's surface that are actually caught up in the magnetic field of the sun. And that energy is traveling through space, and it's coming at us. Without the protective magnetic field, we could have some other problems maybe, being overly bombarded by stuff like that. We'll come back to that idea maybe later in the semester. A kind of a view of, you know, you always show the Earth's magnetic field as a nice, simple, you know, dipolar magnet, like Mr. Wizard with the little iron filings coming around nice and simple. It's not that simple. When we were going to travel into space, we sent satellites up to map it and figure out what is the shape of that and what are the effects on life up there. And so really this is the Earth right here in this little spot I'm pointing to, and the magnetic field of the Earth is constantly shifting. It's kind of like a balloon that if you press on one side of a balloon, it will give in and cave in on the sun side. So the bigger the blast, the more it pushes on that field and warps it. The magnetic storm that affects satellites in space and communications and so on. On the side of the Earth away from the sun, this kind of trails out in kind of long fin-like patterns. And the shape is constantly changing through time. There was a movie out recently, The Volcano. This thing about the coast is toast and volcano. Here's a quote from one of their websites. You know, continents sit on tectonic plates, great big rafts floating over an ocean of molten rock. That's not true. There is no giant molten lake of lava right underneath all of the crust of the Earth. There are little tiny zones in the very upper parts of the mantle where some of it, part of it, is melting. Okay? There are no oceans of molten rock below there. It's kind of how Hollywood takes things too far. So let's take a closer look at this upper part of the Earth and say a little bit more about some of this. I want to introduce some other terms for you. Okay? The outer part of the Earth is made up, you know, the rock portion of that we live on is called the crust. Okay? And below that, by definition, and this information comes from seismology, is the mantle. So we live on this real thin outer part, and we live, of course, on the continents, the continental part of the Earth. And continents are made up of lighter weight, less dense rocks than oceanic crust. Continental crust is mainly granite, mainly granitic type rocks. Oceanic crust is mainly basalt type igneous rocks. So there's a difference, okay? There's another principle that's shown up here I'd like to introduce to you, and that is that the bottom of the crust kind of profile with the mantle somewhat reflects and mirrors the outer part of the Earth, the topography of the surface. If you have a mountain belt, you have a mountain root below it. So as I erode this mountain system down and remove weight and shuffle it off to the sides, then the crust rebounds and comes back up relative to it. That's part of what's called isostasy or isostatic rebound. The concept of isostasy deals with this brittle outer part of the Earth that's kind of floats, so to speak, in a semi-equilibrium with the mantle below it, because there are density differences between the rocks that make up the crust and the mantle. The crust is less dense, the mantle is more dense. Now, crust and mantle are old terms. The newer terms we apply to the outer zones of the Earth are lithosphere and this tongue twister down here, the bottom, called asthenosphere. Kind of phonetically as the no-sphere, asthenosphere. And so crust and mantle are terms more so dealing with the density of rock, a physical property. The terms lithosphere and asthenosphere deal with behavior of the rock, how it can behave under stress, how that it responses, what the strain response is. So the lithosphere tends to be more strong, more solid, and the closer to the surface of the Earth you get, it becomes brittle. It will crack. It will fracture. We call it faulting. And we can get movement along those faults in those places. The asthenosphere is a little more plastic in its behavior, a little more ductile, so it's weaker. It's still a solid. It's not liquid yet. So where's the magma coming from? Something has to happen. We've got to get temperatures hot enough, maybe get a little water involved, lower some pressures, and then we could melt some of this stuff in the upper mantle. So here's more of the guts of where this magma is developing. Now let's go back to one of these plumes, these hot mantle plumes called hot spots. All right, in the bottom right-hand corner, mantle plumes and hot spots. Somewhere in the lower mantle, middle mantle, upper mantle, doesn't matter where it is, we've got this heated up, less dense, solid material slowly rising to the surface as a plume. And it follows up right under here, this volcanic ridge. So as it moves towards the surface, what happens to pressure? Pressure is going to drop. So it's something that's superheated inside the Earth, and you have the pressure drop, because these things are superheated above their melting points. Once the pressure drops, right in this upper little spot, right in here, or maybe up at the top of the screen, right in there, those minerals that have the lower melting points melt. They become liquid. Not all of it, part of it. So we call this process partial melting of the upper mantle. And it's only in localized zones. Sometimes they're long linear belts that we see underneath those mountain chains, or maybe it's very localized, a more fixed, centralized little spot in that case. All right, so now the magma's rising up. Because it's hot, the rocks here will want to also elevate, so topography is higher. All right, so I have an elevated zone, magma oozing out under the sea floor, basaltic magma, because partial melting of the mantle creates basalt. And then it solidifies with that cold seawater. So here I've got this uplifted warm spot. Because it's uplifted, under the force of gravity, gravity wants to pull the rocks away from that ridge down to either side in symmetrical patterns. All right? That's tension. That's a pull-apart tensional force. So the ridge cracks. When it cracks, the pressure drops. What happens? More magma is generated. Squeezes up in the crack. It solidifies. So each time we get subsequent eruption, cooling, and constant pulling. So one of those mechanisms to split this apart, besides uplift and injection, one of the mechanisms to pull and split those ridges apart is called gravity push. It's pushing the idea away from that ridge. Okay? Gravity push is the terminology that they use. We could say gravity pull. We use that for another spot of where this happens. So we're creating this dense basaltic rock. We're creating brand new sea rock material. Let's go to the top picture now. Magma oozes out, and inside basalt is a little mineral called magnetite. What happens to those little magnetic crystals of magnetite in the presence of the magnetic field when this liquid cools and solidifies as a rock? They line up and point to magnetic north at the time the rock solidifies. Okay? Now another eruption takes place, splits it apart, but this time the magnetic field of the Earth had done what? Reversed itself. And then it does it again and again and again. And so in a cross-section view, these black and white stripes represent changes in the polarity of the Earth's magnetic field, and they're very symmetrical. So we have young, brand new rocks here, and they get symmetrically older away from the rift. The magnetic patterns match. Over on the top left is an example of what the seafloor patterns look like, those oceanographers researched, compared to a land sequence of eruptions of lava flows, and they match. So they were able to say, you know, something's going on here. It's the seafloor spreading that's pushing crust, generating new crust towards the continent. So all of a sudden, if this is the Mid-Atlantic Ridge, from this spreading center, it's pushing North America westward. That's Wegener's driving mechanism. That's what was so unique about all this. Now again, the continents are less dense. Ocean crust is more dense. In this particular diagram in your textbook, they're showing where the denser, heavier basalt begins to subduct and go back down into the upper mantle, become reabsorbed, recycled in this convection type of pattern. And so because of that density, once it gets going, gravity takes over and pulls it even more so into there. So that's the gravity pull mechanism that also helps with the movement mechanism for this process. When you can pull downward, you're going to pinch the ocean crust downward. So the steeper the dive, so to speak, of that subduction zone, the deeper that little pull-down zone will be. We call them oceanic trenches. We'll see some pictures later on about the Aleutian Trench. The deepest trench in the world is the Marianas Trench, that's about 36,000 feet deep in the western Pacific. So we're beginning to understand more about mechanisms now of what's going on, mostly from what? Seafloor evidence, along with seismic evidence. The fanciest, newest approach. Remember the picture I just showed a couple of slides ago of that perfect jawbreaker, kind of cross-section of the Earth, perfect circles, concentric circles or spheres? The inside of the Earth is not that perfect in terms of symmetry. And what we're learning about the inside of the Earth is actually coming from a technology with medicine called CAT scans. If you ever had a CAT scan done of your knee or your back or whatever to look at the soft tissues, the concept of a CAT scan is kind of like a three-dimensional view of the inside of your body with detail of all the parts. Well, seismologists took that same idea, took seismic data, which we'll look at next lecture or two, is to 3D model the different velocity zones inside the Earth. So where rocks are really, really cold, velocities are high. Where velocities are, or where rocks are very, very warm, the velocities are slower, and so they would color code the red spots, or the low velocity as red spots, okay, the warmed up zones, and the faster velocities where the rocks are cold in blue. And all of a sudden, lo and behold, we're seeing it's not perfect concentric rings. Maybe compositionally it's close to that, but temperature-wise it's not. And these are all these spots that are sliding and moving around. Cold sinks, warm rises. That's movement. That's part of convection. And that's part of the process that affects that thin, brittle, crackable, movable outer part of the Earth, i.e. the continents. And that's continental drift in that case. I kind of put this inset here. Somebody once out in a western, I think it's Oregon or Northern California somewhere, in a little community, they want to build, they're trying to raise money to build this giant lava lamp right in the middle of their town. We'll have to see. Maybe we'll get to see that in our future on one of our family vacations, eh? All right, so plate tectonic theory came about. And it's believed by most geologists and explains many, many things with a simple model in that case. So I want to use this diagram here to talk a little bit about the earthquakes, because once you move slabs of rock as big as continents around and they split apart, they slide past each other sideways, or they hit head on, our giant demolition derby, we're going to get a lot of problems. We're going to have a lot of rocks breaking, i.e. earthquakes, the vibration of the planet. If there's enough heat built up in some places, we'll have lots of volcanoes. So let's look at this picture. I want to use this map to talk about what kind of plate boundaries we have. The first type of plate boundary on the top is called convergent. A convergent plate boundary is where plates come together. They nearly hit head on. Okay? You'll need to remember these different types of plate boundaries. So convergence is coming together. Divergence is splitting apart, like the sea floor rifts, the spreading centers we just looked at. And transform means that they're kind of sliding sideways past one another. And we'll look at examples of each of these three as we go through here the rest of the day. But I want to point out on this map these dots, all these black dots. They represent a spot on a map that seismologists put on a map. It's called an epicenter. An epicenter is something we put on a map that's positioned on this, it's a spot on the surface of the Earth where the earthquake occurred either right at the surface or somewhere vertically below it. Could be a mile down, 5 miles down into the crust of the Earth. But each of those dots represent, a spot where the earthquake occurred, either right there at the surface or below it at some depth. Now look at the distribution of those. They're very concentrated. This was another thing that they began to understand about, plate tectonics, is that when you plot up all the epicenters on maps, there's a specific pattern there. They plotted up all the volcanoes as well, and a lot of the volcanoes are associated and concentrated in the same places where we find these things. Now look at what's happening up here in Alaska, along Japan, over here on parts of our west coast, the western part of South America and Central America, and compare the number, the amount of dots, the amount of epicenters there as opposed to in the middle of the oceans. There are a lot more dots, a lot more epicenters along these margins. Well, where that's taking place and why is because they're convergent plate boundaries. Where you find most of those clusters, that's where plates are hitting head on, colliding head on. Where they tend to slide sideways past another, we get probably the next major concentration of earthquakes. And lastly, where they're pulling apart and splitting along these mid-ocean rifts or spreading centers is where we get the least amount of earthquake activity, and it's fairly shallow. I have some stars on this figure that show you where some of the plate margins, there's actually 3 different individual plates by names that come together or join at a spot. And we'll look at a couple of these more specifically in a bit. One in particular over here in northeastern Africa. It's called the Afar Triangle, all right? Kind of a triple junction. So where 3 plates come together, 3, we use a statement, triple junctions, where 3 different types of plates come together. And so one over here in northeast Africa, these boundaries here we can see in the central part of the Indian Ocean. There's this plate to the west, this plate to the to the east, and of course to the south. So right there where I'm pointing, just to the right of the star, is a triple junction. There's one over here in the East Pacific. Well, right at that point there, there's a little plate here that I'm pointing to called the Nazca Plate. We'll come back to that name later on. The Pacific Plate, the Nazca Plate, and this little bare spot in here, the name plate, that sounds like a cereal. It's called the Cocos Plate. So 3 different plates are coming together. It's a triple junction. I won't name all the rest of them, but remember that triple junctions are where 3 different plate boundaries come together. And of course, they can be a variety of different types. Let's take a look at some convergent plate boundaries now in a cross-section view. The convergent plate boundaries are where plates are coming head-on. All right? So in the case of this one, we've got the Pacific Plate begins to dive back down into the upper mantle. That's called our subduction zone. If something pushes upward, it's called abduction. We won't look at that too much in here, but subduction. All right? At convergent plate boundaries, the plates are hitting head-on. A good prime example of that today would be the Japanese island system, or the Andes Mountains in South America, or Mount Rainier and the Cascade Volcanic Range that's along our Pacific Northwest up into Canada. Okay? And again, these dots now in the cross sections don't represent epicenters. Epicenter is a dot you put on a map. These dots represent the actual position where the rocks broke and shattered and gave off their energy and vibrated into the earth. In other words, earthquakes. These dots are referred to as hypocenters. Now, if a dot is, if an earthquake or a fracture occurs right at the surface of the earth, then they're the same thing, obviously. But what's unique about looking at these dots in cross-section view is that you can see that you've got shallow clusters, you've got very deep ones, and you've got intermediate ones, and you can draw a line. You could get out a compass and measure an angle of how steeply dipping, how steeply plunging that subduction plate is. Because some of these plates are still hot and they'll just slide right underneath the continent. This one here takes off at an angle, so I've got mantle material. And the Pacific Plate that goes down by the Marianas Trench, I don't have a picture of it for you, but it takes a near vertical nosedive straight back in to the mantle. It's the steepest one on the planet. That's why it's the steepest pinch down or pull down or trench, the Marianas Trench. That trench is deeper below sea than the Himalaya, Mount Everest is above sea level. It's almost 36,000 feet below sea level in the Marianas Trench. So these convergent boundaries are interesting to look at, something that we wouldn't do in this class, but if you're looking for mineral deposits, how wide you can look for in terms of where to find ores, because it's the magmas that come up with this, that are generated here, that bring the gold and the silver and the platinum up and deposit them, or in igneous magmas, in the crust of the earth. And so depending on how wide that is would determine the angle. The steeper the angle, the narrower it is. The lower the angle, the wider it is. The more money and deposits you're going to find. Something that economic geologists would be interested in. All right, here's a divergent plate boundary. Another one, convergent. South America is running into the Nazca Plate. All right, so we get this crumpled up margin or big demolition on the side of South America, head-on collision. But out here in the middle of the Atlantic, this big rift system, we've got this tearing apart process. That's a divergent type of plate boundary. If you could follow that mid-Atlantic ridge all the way up to the northern part of the Atlantic, you can actually go and see what's happening above sea level, called Iceland. There's a hotter, warmer spot under Iceland. And that's why it's buoyed physically and topographically higher. That's why it's above sea level. And you can actually go and hike down the rift and stand on one plate on one side and have another foot kind of on another plate. The actual rift system in that area. So divergent plate boundaries. Let's take a look at that triple junction I was talking about over there in northeastern Africa, called the Afar Triangle. All along the eastern margin of Africa, there's a continental rift system going on. Most rift systems are in the bottom of the ocean today. The East African Rift is one of the rare examples of seeing a continental rift. The Olduvai Gorge if you're into anthropology, is a very good area to study, and it's down in one of these rift systems. So as you trace that rift towards the north, it splits off into the Gulf of Aden and into the Red Sea. So we have the African plate, the Arabian plate, and out here they call the Somalian plate, all right, a small localized plate, and this is splitting apart. So someday, if this split continues, Somalia is going to drift off into the Indian Ocean and become a small continent. It may not. It may quit. It may fail. Whatever's driving how fast that magma is coming up, the activity in the mantle, if that slows down, the rift quits. We'll look at that a little later today. All right? So let's take a look at some pictures of this rifting process up here. Here's a view from space again, the Red Sea. This is Aqaba. This is just the northern end of it. We move a little, here's the Mediterranean up here in the top left. We move a little bit towards the south now in this picture. Here we have the southern end of the Red Sea. This is part of the Afar Triangle and the Rift. Saudi Arabian plate up here on the horizon. So this is part of Africa. And in this rift system, you can actually see black, fresh lavas and all these volcanic cinder cones coming out in that environment. Very coarse-grained rocks. It's splitting apart. Another different view, some more volcanoes, some more lavas. Here's a closer view down the surface in the bottom right of some cinder cones and the rifting. Lots of lavas and Pohoihoi lavas that have come out in this region of the world. So it's a very active rift. It's still going on. Whether it continues, we don't know. We're not going to live long enough to prove it. So Saudi Arabia's splitting apart. The Red Sea keeps getting wider and wider and wider and splitting open, and it's heading northeastward. The Saudi Arabian plate, a little plate, moving northeastward, and it's colliding into this part of southwestern Asia. It's crumpling that zone up. Well, that crumpled up zone is a mountain belt called the Zagros Mountain. So really when you begin to look, we got the big picture in the 60s and 70s. And with the 80s and the 90s, and now in 2000 plus, we're getting more data, better maps, and all of a sudden we're finding lots more cracks and lots of more pieces of the puzzle. So it's not just tectonics, it's called microtectonics. And we're getting better understanding of all of these activities that we can get a better control on trying to predict and therefore tell people to watch out for a geohazard like this. It'll be next lecture, I think we'll get into some more specifics about that. A transform fault is where the rocks will slide past one another. So in this drawing, or this figure, you can see a rift system that's divergent. Here's another divergent, but the whole rift is offset and it's sliding sideways past one another. That's referred to as a transform fault when they go sideways. That's your third type. And probably one of the more studied and dynamic transform faults right now, in at least North America, is the San Andreas Fault. Let's look at this image. All right? If you go down here in the bottom of the Sea of Cortez, or the Gulf of California, between the mainland of Mexico and Baja, went down in a mini sub, you'd see all these little rift systems. All the worm tubes and all the other critters we looked at, lava oozing out. And all of those rifts are offset. All these thicker black lines are transform faults. Now they're all short and stubby here, but all of a sudden you get one big, long one. It starts down here with Mexican border, right here where the Colorado River flows in to the Sea of Cortez, and trace it all the way up to San Francisco. And that long type of trend slip fault is actually, which is we call the San Andreas Fault, which is landlocked, is really a kind of oceanic transform fault that got overridden by the North American plate moving westward. And when you look at this map, you say, boy, there's a lot of faults out here, a lot of little cracks and fractures. Southern California, because it's on the leading edge of a region of crust that's just been involved in lots of collision, is just loaded with fractures and faults and have earthquakes all the time. It's one giant fault, so to speak, completely crushed up kind of zones hidden beneath the surface that we always find out later on about. So try to remember some of the examples of divergent spots, convergent spots, and in the case of this transform fault, the San Andreas Fault is a good transform fault. Structurally, I could probably spend a long time given you hundreds of examples of all these different places in the world where plates have collided. If we take a look at where India landmass broke off from Gondwana land and moved very rapidly northward and slammed into Eurasia, that's why, because it hit so hard, it was the biggest dent, made the biggest mountain mass on land, the Himalaya Mountains, Mount Everest, okay? And it's still going on today. But in slamming in there, as it slammed in, we look on the right-hand side here and slammed in, we get strike-slip motion over here and strike-slip motion on that side, and it's just kind of splayed things out away from it. It's a big impact. And all of a sudden, all those little cracks and faults and movements and earthquake activity become very, very complex and sometimes difficult to deal with and understand. Okay? All right, well, let's move to an idea that deals with some of the plate motion, not so much with a direct convergent boundary, but what happens if a plate is moving across a spot where the hot spot or the plume is fixed in that mantle, and it stays there. As if you were to take a torch and take an old 33 RPM plastic record and slowly move it across the top of that torch, that little blue flame. You'd see a nice line of plastic melt. But if you took the old record and you moved it and jerked it in motions and slowly, fast, slow, you'd see a little bump, then nothing, then a bump, nothing, then a bump. Okay? Well, out in the Pacific Ocean, as the Pacific Plate moves along, it's moving over a fixed hotspot. And what's being created is the Hawaiian, or one of the things being created. There's many other island chains similar to this. One of the major ones is the Hawaiian Island chain. And all of a sudden it takes a little bend right here, just past Midway, and you can trace it northward, and you'll see something happen to these islands. First of all, these age dates on here and plate motions, right now off the coast of the big island of Hawaii, nothing's happening. As far as, that's where the activity is. Okay, you have volcanoes erupting and earthquake activity, all right? And it's brand new fresh rock. It's zero in age. It's brand new real estate. And as the Pacific Plate moves across this fixed hotspot, okay, at different rates of motion, you get a series of islands that develop. And so as you look at the ages of the islands away from that hotspot, they get older and older and older away from it in terms of millions of years of time. And they become more and more and more weathered, lower down. The plate gets what? As it moved across the hotspot, it's hot, so it stays elevated. But what happens to the temperature here? It gets colder and colder and denser, and it sinks. And what happens to a lot of these islands? They get pulled down closer to sea level, right at sea level, get a little coral reef, and all of a sudden they're submerged. So if you trace a lot of these islands, they're all submerged all the way up. These are seamounts. And eventually they're all sucked and pulled back down into the mantle. So there's a number of examples of this intraplate, meaning within a plate, not at the edges, not at the margin of a plate like we looked at, but inside the plate, moving over a fixed hotspot. And one closer to home is Yellowstone. The Yellowstone hotspot is a fixed hotspot in the mantle that the North American plate is moving over. And if we age date those igneous rocks associated with it, the youngest rocks are right at Yellowstone. As you trail on down into the Snake River Plain and move across Idaho and then out into these other states of Nevada and Oregon, of course, the rocks get older and older and older and older. They're the trace of where the plate moved across that hotspot. And today we're looking very closely at this hotspot. I'll bring this back up again because this is an area of concern of a super volcano. Yellowstone is classified as a super volcano. And it had some major, huge eruptions that were devastating. Mount St. Helens, you might remember, and you saw a lot of pictures of it, but Mount St. Helens is really a little tiny thing compared to what happened when Yellowstone blew its stack. We'll look at that again, talk about it later. So, intraplate activity. We also have some other old scars of plate activity we can look at. Remember I said that the East African rift is an active rift? Well, what if the driving mechanisms slow down or stop? the rifting will fail. It will not sink enough and spread apart and become an ocean, will it? Well, there are many, many examples in all of the continents in the crust, in this large demolition derby, that in the geologic past, there were forces trying to rip the continents apart. And I want to bring us in Kansas here closer to home to one of the main ones, okay, that we are living close to in the United States, a failed rift. All right, the acronym for it is CNAR. That stands for Central North American Rift. And if you go up to Duluth, Wisconsin, and along the Keweenaw Peninsula and the northeast shore of Minnesota, you'll find all kinds of basalts and dark other igneous rocks like gabbros that were erupted out of a rift system a long, long time ago. And it was the beginning. It was just like what was going on in East Africa today. But all of a sudden, it quit. It failed. And we can trace this thing now. As you look at those rock types that are typical of a rift system, all of a sudden you drive through southern Minnesota, down through Iowa and Nebraska and into Kansas. At the surface of the earth, you don't see anything. But underneath the ground, a few hundred feet down, 1,000 feet down, through gravity data and magnetic data, this inset on the lower left is a gravity map, okay, showing high density and high magnetic rocks. And we can see that there's a number of these ancient scars or rift systems. There's one down here in Oklahoma, one cutting up this way along the Mississippi embayment. There are literally hundreds of these that make up the old continents because they've been bashing into each other and ripping apart for about 4 billion years. Plenty of time to create some scars. So one of those rifts you can trace below the surface right through eastern Kansas, underneath eastern Kansas. Okay, the CNAR. Remember that. I'll put one of those on the test for you. Getting further south into southern Oklahoma, there's a big rift system, runs roughly east-west. It's not active anymore, but it's an old fracture. There's basalts down there, but it got faulted. And because of all this structural complexity there, there's tremendous oil and gas traps located and associated with the southern Oklahoma allocogen. So here's a new word for your vocabulary, allocogen. It's a failed rift. So CNAR, the Central North American Rift, is an allocogen. The southern Oklahoma structure is an allocogen, a failed rift. And one over here that we look at in southeastern Missouri near a town called New Madrid, the New Madrid Fault System. It's near one of the old oxbow lakes on the Mississippi River called the Reelfoot Lake, or Lake Reelfoot. So because of that, they've called this failed rift over here the Reelfoot allocogen. Now let's look at the orientations of these cracks a little bit, especially the Reelfoot. There's lots of little shattered fragments here, and you can see some of these black lines as faults. North America is moving westward. The North American plate's moving westward. This is an old scar, an old weak zone. And if I were to pull something at an angle, at 90 degrees, it's easier to pull it apart and maybe reactivate it a little bit than it is to move parallel to it. So once in a while, the Reelfoot region has a bunch of earthquakes. The New Madrid Fault. In fact, one of the biggest, in the early 1800s, 1814, 1815, one of the biggest supposed faults that hit North America, based on visual studies, is the New Madrid Fault. The land uplifted and actually changed the course of the Mississippi. Okay? So in the early 1990s, there was concern that all these little micro-earthquakes were picking up over here in New Madrid, and we were going to have a big one again. It didn't happen. But it could. And so a lot of, we're not prepared. Structural characteristics and integrity of buildings out here in the middle of the continent are not prepared like they are in California, where they're always having earthquakes. The engineers build them for those standards. So once in a blue moon, we'll look at these later on again as some specific ones of where there could be some geohazards that affect us. So, here's more of a modern map that we've designed today. Like I said, this is a Nazca, N-A-Z-C-A. Nazca plates moving eastward and South America is moving westward. Big head-on collision. This map has some of the rates of movement and more detail on the positions of things. Here's that COCOS plate, COCOS, as that plate moves northeastward and goes under part of the Caribbean plate and the North American plate. You get all those earthquakes and volcanoes in Central America. So it's the plate boundaries and the activities of the collisions that are causing the quakes and causing the volcanic activity, of which are geohazards that we want to look at. I want to have you think about this one last shot. Here's a shot of Hawaii from space, something to kind of ponder about Hawaii. And think about this, this phrase here, harbor wave. Harbor wave. And we'll come back to that in the next class session. So we'll see you later on. Okay? Thank you.
Thank you.